The first thing you want to do is turn on the laser. You then want to open the VK Analyzer application to access the microscope. And once it's loaded, it will prompt you to center the microscope at the origin, and you'll want to click yes and see it going to the origin here. You then want to place your sample on the sample tray. Use the big knob at first to move the stage in large increments towards the microscope lens. Once the sample comes into focus on the screen, you want to use the smaller knob to do the final focus adjustments. And as you can see on the screen, the surface of the material will slowly come into focus. In most applications, we will use the Measure tab in the top left. The Observe is just for taking pictures, but the Measure will give you a 3D scan of the material itself. You can move around in the application by dragging the mouse or double-clicking to center on something. You can also use the assembly arrows shown in the small window. The first thing you want to do is find your area of interest. Here we have a grid. Since the grid in this instance is tilted, we can use the turntable on the microscope to level it. As you can see here, I'm slowly turning the sample itself on the turntable, and in the application you can see that leveled it. Now we are going from 10 times zoom to 50 times zoom. You want to be careful when doing this as to not touch the lens itself. You can now use the scroll wheel on the mouse to move the center of focus on the surface. The goal is to get the middle of the image in focus. Now in this case we're going to try and image an individual indent. There's an ND filter on this microscope that essentially lets in a percentage of light. For many reflective samples, you want to use a smaller ND filter to let in less light because it can hurt the microscope. You can also use the gain to bring up the brightness of the image. As you can see, there's some small red, which is the laser being too high in intensity, which is not good. The goal is to try and get a small amount of red appearing on the surface of the material. In the top right, it's kind of hard to see, but there are arrows pointing up and down. The two larger arrows will move the lens up from the surface at a faster pace than the one below it, which is a smaller arrow, and vice versa. The ones pointing down will move the lens closer towards the sample. To take a 3D image, you want to move the lens up and down. When you're doing this, you want to make sure to get the material in complete darkness, as this will increment the laser up and down from the top surface to the bottom surface that you set the position in. We skipped over the process of the image incrementing the laser and stitching it together. But after we've done that, you'll want to click Finish, read the prompt, and click Yes. This will then prompt you on where you want to save your image and what the file name you want to be. It'll then open up a analyzer, but in most cases you want to use the multi-file analyzer as it has more functions. You'll click Add Data, go to where you saved your data, and import that. You will then want to click on the image that shows the height of the material. As you can see, there is somewhat of a gradient, meaning one side of the surface was higher than the other side when the image was being taken. You'll want to filter this out. You'll click on Perform Filtering and click Reference Height. And then you will then move the crosshair and try to get the blue lines on the right and bottom of the image to be as smooth as possible. In this case, we moved the crosshair off the grid to avoid any surface roughness. It will then process the data, and as you can see, it filtered, so it looks much better than the gradient before. This is the 3D image viewer. You can tilt the surface itself, and you can use the height magnification to make the surface more prominent. There are then many different analyzing tools that you can use. For example, you can do a line roughness. You can place the line on one point in the surface and then click on another point to make that line go fully across the surface. In many cases, you can use this to measure the pileup of an indent. As you can see, there is a slight increase in height before the indent, which is indication of pileup. Another thing you can do is to use multi-lines, which will give a average of the line roughness. In most cases, you don't want to do this on indents and want to use it more in plane surface areas. Another thing you can do is surface roughness. You take an area of the sample, and there are many different shapes options you can use. In this case, we are using a rectangle. You want to find somewhat of a flat area. Click OK, and it'll measure the average surface roughness in that area. And if you want to be more accurate, you can use more squares and get a better average. Something else you can do is profile, which is similar to line roughness. You'll click a point and then click another point, and it will give you the profile data from that segmented line. In this instance, we can see the indent, and you can see a much more prominent pileup before the indent. You can move these lines around after you set them to find your more desired position. Some other thing you can do is compare, which is comparing two different measurements. You can also do a height step, which will show you the max and the min height in a certain area. This is helpful to get the lowest point in a surface, such as an indent. There are measurement and volume options, which you can do as well. You can also add many more data into a single multi-file to compare your different datas and keep everything nice and organized. Before you exit this out, make sure you save it. It will prompt you to save in the location you want, and you can input a name. Another option you can do is to measure on the actual sample itself without taking an image. Here we are measuring the distance of an indent by using the line measurement. Another ability you can use with this microscope is to stitch images together. In this case, we want to get the whole grid, and we are in a high enough magnification that it cannot fit all in one image. We'll go to the assembly window, click create an image, and then capture in a wider field of view, which will move the microscope around the center image. You can now select the places you want to image. In this case, we're only going to do 2 images of the top left 8 indents. You can do much larger images depending on what you want to image. This will then ask you to save the stitch before it starts stitching images together. In most cases, you want to use the automatic settings, and you do not have to set the lower and upper positions. The reason you would want to zoom in closer than zooming out and taking an image of the whole grid is to get a much more detailed image. As you can see, once the process is completed, it will pop up with a window where it will do the final stitches. You can position it manually, but the easiest way is to press execute all, and it will stitch the image automatically together. Usually there will be an error showing that the image is too large. It is okay to click OK on this. You now have the option of increasing the image resolution or decreasing it, depending on how large you want your image to be. This will also contribute to increasing the quality if you increase the resolution. Once the image is processed, it will pop up in the microscope application and a scale will pop up. You can move this wherever you want. In most cases, we want to move it in the bottom right-hand corner of the image. There are different view types you can select. For example, height, optical, laser, and laser optical. When you click finish, the data will save in the allocated file. You can then go back to the analyzer application and upload the stitch you just took. This process is the same as regular images. In this case, you'll want to filter the data again, as there is a height gradient when the stitch was being taken. You can then view the stitch in 3D, just as you could with the regular image. You can perform all functions of the microscope with stitches as well. Before taking off your sample, you want to put the microscope back on 10x in order to keep the lens as far away from the sample as possible. You then want to exit out of the microscope application, and that will automatically turn the laser off.